This is section 361, and it's a discussion about composite functions and what we do when we find ourselves with composite functions in calculus. So if you remember, a composite function is taking one function and putting it into another. So for instance, this notation here, f of g of x, is where we put, since g of x is inside f in the notation, then that means we put function g inside function f, which means if g of x is x plus 2, we got to put it here and square it, and we got to put it here and multiply it by 5. So it looks something like this. We take g of x squared plus 5 times g of x minus 3. And so take a second to simplify that. So you might want to stop the video at this time to do that. So if we flip that up, then if we look at this notation, it's taking function f of x and putting it into g. So here's function g, so we're going to put f into g, which means where we see this x, we're going to put this whole trinomial x squared plus 5x minus 3 into here, and that's going to look like this. So it's going to look like x squared plus 5x minus 3 plus 2. And then again, take a second to simplify that. So you might want to stop the video at this time. At this time, you're going to be doing an activity, and so you can either do the activity, you can either pause this video and do the activity on your iPad in Notability, or you can print out the activity and do it with pencil and paper. So let's take a look at that activity. The activity is exploration 17, and it's discovering the chain rule. So at this time, if you don't have this in front of you, then you might want to stop the video and go ahead and print that out, or locate that in the materials folder and get that loaded onto Notability. And then once you do, come on back here and we'll do the first one together. Just to get you started on the activity. Okay, as of now, I'm assuming you have the exploration sitting either in front of you in paper form, or you've got it on your iPad ready to start it after you see this short introduction. So let's say we have this original function x to the 6th power. We know how to take the derivative of this, right? It's just a power rule, right? Bring the 6 down. It'd be 6 times x to the 5th power, reduce that power by 1. But we can write x to the 6th these two ways. We can say x squared cubed, so this is also x to the 6th, right, because it's x squared times x squared times x squared. Or we can write it as x cubed squared. In other words, we could say this is x cubed times x cubed. Either one of these is the same as x to the 6th. So we know if we differentiate this, either one of these functions g, we should get 6x to the 5th. That's what the derivative should be. We know this because we're looking at the derivative right here. So both of these are composite expressions. We have an inside function, x squared, and an outside function, which is something cubed. And likewise here, we have an inside function, something cubed, and an outside function which is squaring that. So just like the introduction with composites, putting one function into another. So we're going to start by taking the derivative using a straight power rule on the outside power only. So in other words, here's the outside power 3. I'm going to bring it down. I'm going to rewrite this. I'm not going to touch it, but I'm going to reduce this power to a 2. That's the power rule, right? Bring the original power down, make it the coefficient, or multiply it times any existing coefficient out there, and then reduce that power that you brought down by 1. So it looks something like this. Brought down the 3, we didn't change the x squared, so the x squared is still the same. We're not touching the inside at all, but we have a new power on the outside, which is squared. So if we simplify this, we know we have 3x to the 4th power. Well, that is not this. So we can agree that just doing the power rule on that outside power isn't getting us the derivative. So let's try let's look at then what we're missing here. So we need a 6. we have a 3, so we're missing a 2. And we need an x to the 5th, and we have an x to the 4th, so we're missing an x. So we're missing a factor of 2x. And so if we had this extra factor of 2x and we multiplied it by 3x to the 4th, then we'd get x to the 6x to the 5th. So we're missing that factor. So we have to figure out how we can incorporate this factor so that we can get the right answer. So what you're going to do is you're going to try doing this with g of x being x cubed squared. You're going to bring down the 2, and you're going to leave this alone, x cubed, and then this is going to become a 1. Okay, and then go ahead and try that with the rest of the functions and see if we can. After you do that, you're going to try to figure out what's missing. So that, what factor is missing to make it 6x to the 5th, because you know this is the right answer. And then you're going to try that for some other functions as well. So in this case, we get 2x cubed, right? Bring down the 2, leave the x cubed by itself. We're not touching the stuff inside the brackets. And then reduce the power to 1, that's 2x cubed. So it looks like we're missing a factor of 3 and x squared. Okay, so go ahead and complete the rest of the examples. Try to find a pattern here, like it says in your activity. Try to find this pattern, where this is coming from, and try to draw a conclusion. And at this point, you might want to stop the video and accomplish that. And the next couple of screens will be going through that activity. So it's best if you complete the activity first and kind of compare the results to what we have. So after you've concluded the activity, taking the derivative of all the functions, all the f of x functions, and then doing the outside power rule on all of the g of x functions, what we notice is that to get our correct answer, the correct answers are all in green. We know that these are the derivatives. These are equivalent composites, mathematically equivalent. In order to get the correct derivative, our missing factor, if we look back into the original composite function, our missing factor comes from taking the derivative of what we call the inside function, or the function inside the brackets here. So this 6x squared is the derivative of this. This 4x cubed is the derivative of this. So if we take the derivative of the outside times the derivative of the inside, we can then get the derivative of the function if we would not write it as a composite. So, and this becomes really helpful for this last one in particular, where we have this trinomial and we can rewrite it as a binomial squared. So we can, in essence, we can factor it. And this is where this process becomes really helpful, because taking the derivative by bringing down the 2 times 5x plus 2 to the 1 power, and then just times the derivative of the inside, which is 5, is a much easier way of taking the derivative, especially if this power up here is like 3 or 4 or 5 or 6, where you don't want to do all that foiling. So our conclusion is that the missing factor, oops, I misspelled that, should be factor, is the derivative of the function inside the brackets. The chain rule, and the chain rule kind of like links on a chain. The chain rule kind of links one derivative to the other, to the next, to the next. And then with that, since those derivatives are all part of a composite, we can multiply them all together to get the appropriate derivative. So the way we define the chain rule then is that we have a composite function here. So this is a composite function. And in this composite function, we have an outside function and an inside function. And then we call this inside function u of x, or u. We call the inside function u. And so g of x, which is the inside function, we set equal to u. And then we can rewrite the outside function f of u instead of f of g of x. So this becomes, the outside function becomes this function that is written in terms of u. And then, so like we found out in the investigation, if we take the derivative of the outside, which is this, and we take the derivative of the inside, which is this, and we multiply them together, then we can get the appropriate derivative for the original function, the original composite function. And so our essential question today is, when is it appropriate to use this chain rule? So for instance, if we look at this first example here, we've solved problems like this and found derivatives before. So we can FOIL this out, and then we can use our power rule to find the derivative. So our derivative here would be 8x plus 12. We know this is true. Foiling something squared is a pretty quick process. So we know using the power rule that this is definitely the derivative. But if we take a look at this expression, y equals 2x plus 3 quantity squared, and we use the chain rule, what we do then is we look for an inside function. We look for a composite expression. And so our composite expression looks like 2x plus 3 inside of u squared. So we're going to call u 2x plus 3. And we call that the inside function. And then that means if we rewrite y, we get y equals u squared. So here's my outside function in terms of u, and here's my inside function, which is in terms of x. So when we take the derivatives of each one of these things, the derivative of y with respect to variable u is 2u, that's the power rule. The derivative of u with respect to variable x is 2. And we know that when we take the outside and the inside derivative and multiply them together, dy du times du dx, we get the correct form of the derivative. So our correct form of our derivative is 2u times 2. And of course, since we're finding the derivative of y with respect to x, that's our function, our original function, we need to put this back in terms of x. So what we're going to do is we're going to substitute back in our inside function 2x plus 3 times 2. And so if we distribute all of the factors across the brackets, we get 2 times 2x is 4x plus 6, but we have more distribution here. So we have 8x plus 12, and that is the derivative. Using the chain rule, we can see it that matches our original derivative that we know to be true. So that's kind of how the chain rule works. And really the benefit here on this problem, there's not too much of a benefit. So the next question then is, what is the derivative evaluated at -1? That's what that's saying. What is y prime of -1? In other words, what is the derivative of y, right, y prime, and evaluate at -1 means find the derivative and stick -1 in there. And then I want you to write the equation of a tangent line to that curve. So we're going over the skill, and we'll go over the skill every unit, almost every day. It's a really foundational skill. It's a part of every calculus problem we'll do for a semester. So we need, if we want an equation of a tangent line, we need to find a slope and a point. So here is 2x plus 3 quantity squared. We want the tangent line right here at -1x is equal to -1. So the first thing I'm going to go find is the slope. And when I say slope, I'm thinking derivative. So taking my derivative here, plugging in -1, 8 times -1 plus 12 is 4. So I know my slope is 4. Now I need a point. When x is -1, if I put -1 back into the function, 2 times -1 is -2, plus 3 is 1, 1 squared is 2, so our y is 1. Now I can take this information and put it into slope point form of the equation. So I have y equals 4x plus 1, because it's x minus -1, and then plus 1 on the outside. So we have a tangent line here with a slope of 4, going through point -1, comma 1. We can see that the intercept is 5, and if we simplify this, we see an intercept of 5 as well. But we like to leave the equation of the line in this form. It's a big time saver. So looking at the next question, this is where the chain rule really is beneficial. Because if I asked you to FOIL this out, it would take a long time to FOIL something to the 5th power. So that's ridiculous. We're not going to waste our time doing that. we're going to use the chain rule and get this answer really quickly. So in using the chain rule, we've got to realize that this is a composite expression. So we have an inside function of 3x squared plus 4. So that's what we're going to call our u. And so our outside function then looks like 6u to the 5th. And now we're going to take the derivative of each. I'm using prime notation here just to make this a little more compact. So taking the derivative then of 6u to the 5th gives us 3u to the 4th. Taking the derivative of 3x squared plus 4 gets us 6x. And we're going to go ahead and multiply our outside derivative times our inside derivative. And that's our derivative dy dx. And then we're going to write that back in terms of x. So we're going to substitute the u back out. So remember u is 3x squared plus 4. So that's going to go right down in there. And then times 6x, that's our inside derivative. And then we're going to re-express that. So dy dx equals this 30 times 6x is 180x. We're going to put that out in front. And then we have 3x squared plus 4 to the 4th power. So that's the derivative of y with respect to x. We do not FOIL this out. That's the whole idea of the chain rule, is to save us time and so that we can avoid FOILing. So the only downside is that I have to take my word that this is in fact right. We're not going to FOIL it out and check it. That would take too much time. So let's apply the chain rule now to something that has a trigonometric function in it. And so when we look at the chain rule here, again, we're looking inside the brackets, basically. There's my inside function. So my inside function is x to the 4th over 2 minus x cubed. My outside function then becomes y equals cosine u. And when I take the derivative, I like to rewrite this to use the power, so I can use power rule and I can see it a little more easily. So I'm rewriting this. Instead of x to the 4th over 2, I'm going to call that half x to the 4th. So remember, dividing by 2 is like multiplying by a half. Now I can take the derivative more confidently by bringing down my 4. 4 times 1 half is 2. And then my new power then is x cubed. And then I have a minus sign. And then doing the power rule here, I get 3x squared. So there's my du dx. That's my inside derivative. My outside derivative, dy du, is the derivative of cosine, which is negative sign times negative sign of u. So my derivative here, dy dx, then is dy du times du dx. So my outside derivative and my inside derivative. If you notice, if we think about these as fractions, see how the du cancels and we end up with just dy dx. So we can always use our kind of canceling ability of multiplying fractions to see that I've written that correctly. So my dy du is minus sine u times du dx is 2x cubed minus 3x squared. And notice I've added brackets here because that whole thing has to be a group multiplied by the sine function. And then I'm going to substitute out the u. So get my original inside function there. And then that's the inside derivative. And now I'm going to rearrange this because this polynomial really should be out front of the trig expression so that we don't mistake it for being inside the trig function. So it would be minus 2x cubed minus 3x squared, that quantity times the sine of this angle, x to the 4th over 2 minus x cubed. So that's the derivative of that trig function. Now we're going to evaluate it when x is equal to 2. So here's that trig function, just like we wrote on the previous screen. I'm going to take out all the x's. I'm going to put 2's in. So I'm going to have 2 cubed here. And this one I'm going to have 2 squared. And then inside the sine function, I'm going to have 2 to the 4th. And then over 2, then minus 2 cubed. So when we evaluate things, actually with trig functions, what we want to do is, I'm not going to worry about this right now. I'm going to focus on evaluating the trig function first. So 2 to the 4th is 16 divided by 2 is 8. And 2 cubed is 8. And 8 minus 8 is 0. And sine of 0 is also 0. I know this whole thing is 0 without even evaluating this. So I don't bother evaluating that. So always go after that trig first. It might save you some time. So at this point, you can try these 2 problems or the next 2 problems in your notes. And the solutions are on the next video, the day 2 video. But try these on your own and stop. So stop the video right now and try them. And then when you start the video back up again, you'll see the answers for each one of these problems. But if you can do these on your own, then you're doing really well. So if you're tuning back in now, I'm assuming you've tried both these problems, and here are the answers down below. The full solutions are on the next video for day 2 if you would like to look at the full solutions. At this point, you should be able to do the day 1 homework. Don't forget to go back and finish up other WebAssign. And don't forget, you always have the opportunity to level up on con quizzes, and then you also have the opportunity to polish off your algebraic skills by doing that remediation from the previous unit.